Greetings. In today's video, we will be talking about a simple DC series circuit and doing a little analytics with Ohm's Law and Kirchhoff's laws. This is sort of going back to my roots. I started out doing electronics back in the 1960s with similar circuits, similar calculations. Interesting times back then. We didn't really have any computers. What I had was a box of electronic parts, a couple of plastic breadboards, some battery holders, and a pretty cheap multimeter. Yeah, fun times back then. And of course, if you're doing work on electric circuits back then, you spent a lot of time in the library because you did not have a parts catalog, and they were usually in your public library. And again, no internet, no computers, so you went down to the public library, you got the catalogs, you searched through them for the parts you wanted. Photocopies were expensive, so you usually had a couple of those black composition books and a couple of number 2 pencils, and that's where you recorded your data. It was, like I say, it was an interesting time back then. Things have changed considerably. Anyway, in this video, I'm getting back to my roots, what I started with originally, so hope you enjoy it. Before we get started, a couple of announcements. I posted a survey in the community section, just trying to get opinions of viewers on what they want to see in future videos. Please take a moment to fill it out. I've also created a companion post at retiredtechie.com for this video. I'm going to try making a habit of that, doing a video as well as a companion post with additional information and such not. We'll see how that goes. Oh, and I did hit 500 viewers, so I want to thank you all for viewing and subscribing. It's a great feeling. Like I said, I didn't expect to get anywhere near that. This is more of a personal project. I'm doing it because I enjoy it, so I don't have a fancy studio or fancy equipment. I'm working with what I got. But thank you all anyways for taking the time to subscribe and to like and to leave comments. Anyway, let's get on with the video here. All right, let's start with Ohm's Law. Ohm's Law is named Ohm's Law was created by George Ohm, a German, a couple centuries ago. He did experiments with chemical batteries. Not going to go down that rabbit hole, but he did notice a relationship between voltage and current and resistance, and that's what we call Ohm's Law. So Ohm's Law explains the relationship between voltage, current, and resistance in a circuit. It's one of the basic things that most people, when they start studying electronics, learn. Lots of people tend to go over this particular formula ad nauseum. I will say there has been rare occasions when I've actually had to do calculations, but for the most part, for me, it's been understanding the relationship that's helped, not the actual calculations. As I said, the majority of the time, it's simply understanding the relationship. So basically, one of the 3 values changes, the others will change to compensate, but understanding the relationship allows you to figure out what caused the change. And that's something you get into a little more when we talk about troubleshooting. But in the beginning, I gotta say, one learns the relationship by doing the math. And this is mostly a paperwork exercise. So our first of our 3 values is voltage. This is represented by V, at least that's how I'm representing it in this video, though you may see it represented as an E for electromotive force. It's also used, it just depends on what book or what video you're watching. So either or. If you want to get into the physics of it and the math, 1 volt is equivalent to 1 joule of work per 1 coulomb of charge. And again, rabbit hole I'm not going down. Unless someone's really interested, that's a whole video unto itself. But I've never found this level of detail necessary. Well, other than having to pass a test in college. Actually, having to pass several tests in college, but yeah. Never in the field have I found this level of detail needed. So just think of voltage as an electronic pressure. Our next value is current, and interestingly, current is represented by a capital I. This is from the French intensité du courant. I'm probably butchering the pronunciation of that, but we get the I from a French pronunciation, well, from the French anyways, so that's where the I comes from. But current is pretty much, when we're talking about it, represented by an I. As with voltage, one can get deep into the physics and the math of the whole current thing, other than to say current is 1 ampere is basically 1 coulomb. Current's measured in amperes, but it's 1 coulomb of charge passing a specific point in 1 second. The other thing I need to mention here, since we're talking about current, is hole flow versus electron flow. I'm using electron flow in this video, which means current flows from negative to positive as electrons leave the negative terminal and jump from atom to atom all the way around to the positive terminal, whereas hole flow is another concept where it's the absence of electrons we're tracking. So electrons jump from one atom to the next. The hole that was where the electron jumps into is now at the previous atom. So if we're talking hole flow, it's positive to negative is the flow of current. There are some places where this makes sense to use, but for the most part, we're going to be using electron flow. So current flows from negative to positive. For practical matters, think of current as electrical flow, and it's measured in amperes. Now, our final element is resistance, represented by an R. That makes sense. It is a measure of a material's resistance to the flow of electricity. In other words, how hard or difficult or how easy it is for atoms of particular or molecules of particular material to give up their electrons. Anything with a high resistance does not like to give up its electrons very easily. Anything with a low resistance does like to give up their electrons. Resistance is measured in ohms and is the equivalent of voltage, electrical pressure across an object, divided by the current flow through the object. So that's the basic relationship. And this is what we call Ohm's Law, because there's 3 different sets of values we can derive algebraically, that math stuff again, 3 equations. So let's go over them. The first one I always tend to remember is V equals IR, or voltage equals current times resistance. If we do a little algebraic manipulation, we can say current equals voltage divided by resistance, which means, well, voltage is proportional to current. It's also proportional to resistance, but in this I equals V over R. Current is still proportional to voltage, but it's inversely proportional to resistance. And the final equation, R equals V over I, or resistance is equivalent or proportional to voltage, but inversely proportional to current. But these are 3 equations we use in Ohm's Law. Next off, we want to talk about Kirchhoff's law, which is Gustav Kirchhoff. Again, another one of those early pioneers of electronics. So Kirchhoff's law, basically, there's 2 of them. And to actually use Ohm's law, we need to understand Kirchhoff's law. So Kirchhoff's first or current law states that at any circuit node, the sum of the current entering and leaving the node is 0. The implication of this is in a series circuit, current is the same all at every point in that circuit. Kirchhoff's second law is his voltage law, which states that in any circuit a series circuit, we're talking about the sum of all voltages around the closed loop is 0. So if you have a power supply producing X voltage, then whatever your load is has to also drop X voltage to be 0. Before jumping into actual circuit analysis, let's talk about direct and alternating current. These are the two ways of commonly describing electronic current, like I say, direct and alternating. With direct current, current always flows in the same direction. As I said, it can be described as electron flow from negative to positive or hole flow from positive to negative, but it's always in one direction. Alternating current, on the other hand, shifts direction periodically. For example, in the United States, household outlets produce 110 volts AC at 60 hertz, which basically means the current switches direction 60 times a second. If you're in the Philippines or Europe or some of the other countries, it's 50 hertz or 50 times per second. But yeah, there are advantages and disadvantages to each form. Most of your electronic component devices are going to be using direct current. The advantage of alternating current, well, basically if you want to send direct current over a long distance, you can't. It's very limited how far you can transmit direct current through a transmission line, whereas alternating current can be sent much, much further. So current is delivered to your house as AC because that can be transmitted great distances, and you have power supplies in your devices which convert it to DC, which can do all the cool stuff you need to do. Okay, let's do our simple circuit example here. We're going to demonstrate Ohm's Law. It's a series circuit consisting of a direct DC source, battery in this case, and a load resistor. Pretty simple. Additionally, we will use the power formula after we do the Ohm's Law calculations, just because they're usually done at the same time. Power formula is usually taught at the same time as Ohm's Law, even though it's not. So here's our circuit. You can see on the left-hand side, we have our power source, 1.5 volts. This is like, say, a AA battery. On the right side, we have our load indicated by a 100 ohm resistor. That's the symbol for ohm there, the omega. And I, we show our current flow going from negative to positive. So our first job is to calculate I. And if you recall from when we went to the three equations, I equals current equals voltage over resistance. Therefore, we can say current equals 1.5 volts divided by 100 ohms. I told you this was going to be simple. And this gives us a current of 0.015 amps, or 15 thousandths of an amp. Or to shorten it, current is equal to 15 milliamps, the milli being thousandths of an amp. That was pretty easy. So now let's jump over to the power side. So the power equation is P equals VI. We've calculated I. We've got V. We could do it straight out right here, easy. But we're going to have to do this a little more roundabout, more math stuff, but just to prove a point. Well, not really to prove a point, but just we're going to do it a roundabout way. So we're going to assume we haven't calculated current yet, but we do have voltage and resistance. And from the previous example, we know that the current I equals voltage over resistance. So we can substitute within the formula for I. And we get power equals voltage times voltage over resistance, as we substituted that for I. Simplifying, power equals voltage squared over resistance. So we can say power equals 1.5 volts squared over 100 ohms. Or more specifically, power equals 0.0225 watts. Or we'll use the milli designation for 22.5 milliwatts. For 22, we'll use the milli designation for 22.5 milliwatts. Okay, that's about it for this video. Thank you for watching. I hope it was educational. It was, like I say, a simple analysis of a series DC circuit with a power supply and a single resistor. Again, back to my roots back in the 1960s when I started all this technical stuff. Who knew then it was going to lead to a career? Anyway, thank you for watching. If you'd like to see more of these type of videos, let me know. I can do more. I think I'm going to do a couple more of these. I'm trying some new formatting and new editing techniques, so we'll see where those go. But yeah, maybe once a quarter I might want to do another one of these electronics videos. It's getting a little more complicated each time around, unless people really want to see more of them. It was fun doing this one. We'll see what the response is. Anyway, I want to thank everyone who's subscribed, because like I said earlier, I hit my 500 mark. That's great. So if you enjoyed this video, please comment, like, subscribe, all that kind of YouTube stuff. And again, let me know what you really want to see. I all sorts of videos I want to do, but I just thinking about what people actually want to see, and I want to at least, I could do videos I want, but a lot of people probably wouldn't be interested. So let me know. We'll see how it goes. Anyway, next time around.